every single injection event, every valve timing calculation. Basically, every piece of synchronized control on the massive Caterpillar C175 engine depends on the ECM knowing something with absolute, pinpoint precision. It needs to know exactly where the crankshaft and camshaft are at any given microsecond. And honestly, here is the kicker. That crucial information, it doesn't come from some battery-powered sensor. It actually comes from the gear teeth themselves, generating their own electricity as they physically spin past a magnet. It's brilliant engineering. So let's dive right into this explainer and decode exactly how this engine's speed and timing sensor suite really works.
Here's our roadmap for today. We're covering engine position and speed, the 3-sensor array, variable reluctance explained, reading the AC signal, and we'll wrap up with troubleshooting sensor faults.
Okay, Part 1. Engine position and speed, the need for absolute precision.
Now, precise speed sensing is literally the bedrock for engine synchronization. If you get it wrong, your fuel management and your air management just fail entirely right along with it. But here is the mechanical paradox we have to deal with. Most people just assume every ECM sensor gets a standard 5-volt supply straight from the computer, right? Well, these speed and timing sensors don't receive any battery power whatsoever. Zero. So, how exactly does the computer get this incredibly vital data without actually powering the sensor?
Let's move to Part 2 to find out. The 3-sensor array, built-in redundancy.
Cucked securely right inside the engine crankcase, over towards the left rear section, is the primary speed and timing sensor. That's part number 244-5544. This primary sensor physically watches the teeth of the crankshaft gear flying by, and it acts as the main voice telling the ECM exactly how fast the crank is actually turning.
But it absolutely doesn't work alone. This is a redundant 3-sensor suite. You've got that primary sensor on the crankshaft, sure, but you also have a secondary sensor plus a tertiary backup sensor sitting on the top rear portion reading the camshaft gear. To even initiate a start sequence, the ECM is going to demand clear signals from at least 2 of these sensors. But once it's actually running, the C175 can keep operating at its rated speed even if 2 of those sensors go down completely, and it only has 1 single signal left. Talk about a failsafe.
And there is this absolutely incredible piece of mechanical trivia regarding how the ECM finds top dead center. A single tooth for both of these gears has deliberately been partially removed. So the ECM watches the gear teeth fly by, right? And when it spots that specific missing tooth, it flags that exact gap as its timing reference point. Meaning, the engine calibrates its timing offset totally automatically on every single startup. No manual calibration needed. All right, Section 3. Variable reluctance explained. Self-generating signals. Okay, let's finally solve our unpowered sensor mystery. A variable reluctance, or VR sensor, is a completely passive device. Inside, it just has a magnet and a coil of wire. That's it. As the iron-based gear teeth pass near the sensor's magnetic tip, they physically disturb the magnetic field, and that disturbance induces a tiny voltage pulse inside the sensor's coil. So the motion of the gear teeth is literally creating the electricity. No external voltage required from the battery at all. If you're having trouble visualizing this, just think of an old-school bicycle dynamo light. There's no battery involved, right? There is just a small generator rubbing against the spinning wheel, and it produces light purely from that spinning motion. The faster you pedal, the brighter the light gets. That is exactly how a VR sensor operates in the harsh, high-vibration environment of the C175. The spinning gear teeth generate the signal themselves, and because there's no external power supply circuit needed, well, that's just one less thing that can break.
Section 4. Reading the AC signal. Data from motion.
There's a really direct proportional relationship at play here. Every single time a tooth passes the sensor, it creates a small voltage spike, making an AC waveform. At lower engine RPMs, the gear teeth pass less frequently, right? So that gives you a lower frequency AC signal. But as the engine revs up, those teeth pass way faster, spiking the frequency. The ECM simply reads this frequency to calculate engine speed, and it counts the individual pulses to determine precise rotational position.
Which brings us to Section 5. Troubleshooting faults. Theory meets reality.
Let's take all this theory straight to the shop floor. You absolutely cannot mistake a variable reluctance sensor circuit for an active pull-up voltage circuit. Active sensors use a 5-volt supply, meaning if a wire breaks, the ECM just sees a flat 5 volts and throws a voltage above normal code. But remember, our passive VR sensors generate their own AC signal.
You can't just poke at it with a multimeter looking for 5 volts DC. You need to hook up an oscilloscope to actually look at that AC waveform.
And that gives us a super actionable rule of thumb to remember. Let's say you connect an oscilloscope to a crank position sensor while the engine is actively cranking. If, instead of a nice wavy AC signal, you just see a dead flat line, you do not have a mechanical engine speed problem. Because VR sensors generate their own signal purely from movement, a flat line while the engine is physically turning over guarantees you have an electrical break. It's either a bad wire somewhere or a failed internal coil. Let's just lock in that diagnostic workflow with 4 quick steps. Step 1. Connect your oscilloscope to the VR sensor circuit. Step 2. Crank the engine over and watch closely for that AC frequency waveform. Step 3. If you get a flat line, grab your multimeter and confirm the wiring harness actually has continuity and no shorts. Step 4. If the harness is perfectly intact but you still have 0 signal, you know exactly what the problem is. You replace the sensor, because that internal magnetic coil has officially failed. It's a simple process of elimination, but it's totally driven by a deep understanding of how the component actually works.
So the ECM is honestly an absolute marvel. It takes these tiny, self-generated AC pulses from spinning gear teeth and translates them into microsecond perfect injection commands. But I want to leave you with a final, kind of provocative thought. If the engine's entire operation relies so heavily on the ECM processing this exact sensor data, what on earth happens when a catastrophic system failure occurs and you literally need to bypass the ECM completely just to save the facility? How do you manually override a computer that controls absolutely everything? Well, that is exactly what we're going to explore in our next explainer. Thanks so much for hanging out, and keep learning.